Section 5.4, Sampling Distributions and the Central Limit Theorem. Sampling distribution is saying what sample can we take out of the population. Sampling distribution, the sample mean. Basically what we're looking at here is I've got a Venn diagram, and let's suppose it's my entire population. It could be the population of all the various students. I can take a random sample of those students, and there will be infinite random samples based on size, and those will vary somewhat. Random sample 1, random sample 2, random sample 3. But in the end, they're all going to come within a certain similarity, regardless of the sample. No matter what sample I take, it'll become within a certain similarity to each other. Whether it's height, whether it's weight, whether it's number of people who own cars versus don't own cars, what people are majoring in. On average, a sample from a population, every time I take a different sample, it won't vary much. That's why I can use a sample as a good example of what the population is. I don't have to talk to all 330 million people in the United States. I can talk to 1,000 of them. That's a sample of it. If I do a different 1,000, I get the same kind of information. It may not be exact, but it's pretty close, and we get an idea of what the population looks like by looking at the sample. Now I want you to look at this formula here. The mean of the sample mean, we're going to assume the sample mean, that sample of people, is the same as the population mean. But the deviation is going to change slightly. This is called the standard error of the mean. If we have given a population deviation, we are going to divide it by the square root of the number of samples. This is actually pretty simple. Now, I want to talk a little bit more about the Central Limit Theorem first. And I'm going to go back to this and see where this comes from. If I had 4 people I surveyed and how often they go grocery shopping, and they could either go once a month, 3 times a month, 5 times a month, 7 times a month, and I select any 2 individuals of these 4 individuals, these are all the combinations. This is no different than the number of pennies being flipped we've talked about, or the variations within binomial probabilities. I won't read through all these, but you can see how I arrived at this. One of my samples of 1, that means one individual shopped once a month, second individual shopped once a month. And there's a total of 2. So how many times do they shop a month on average? Well, 1 plus 1 over 2. That's 2 over 2 is 1. If I go to the bottom, bottom left, one person could shop 3 times a week. Another person could shop a month. The other person shops 7 times a month. 3 plus 7 is 10. Divide by 2 with 2 people I've selected. That's 5. 5 times a month on average. Or I can go to the upper right here where I've gone one person shops 5 times a month. The second person shops 1 time a month. And 5 plus 1 is 6. Divided by 2. That's the average of 3. So these are all the combinations for just 2 people shopping either 1, 3, 5, or 7 times a month. And like we did before, the frequency of only each shopping on average once a month is 1/16. The frequency of the average of shopping twice a month on average, it would be 2 out of 16. We've added all these up. And in the end, this is all the frequency. The most common type is 4 times a month on average. And if I add 1/16 plus 2/16, 3/16, plus 4/16 plus 3/16, 2/16, 1/16, that adds 1. That's 16/16. And again, you see the bell curve forming here. This is a binomial distribution. While there could be infinite combinations, they tend to cluster, and there's more variation within as we get more combinations as we get closer to the center on each edge. We don't know how far out the variation goes and what the mean will be, but this is how, with the infinite combinations, they usually cluster towards the middle. And as we did last week also, I have a 1/16 or 0.0625 possibility of getting any combination. But when I figure out the standard deviation, it's 4, as we did. And then the variance, we use our formula from before, where my sample, individual sample minus my mean squared times the probability of each one of those, it will equal 1/16 on average. But when I multiply those out for the probabilities in general, I can find out what my variance is. My variance, after add all these up, equals 2.5. Square root of that, which standard deviation is 1.58. Now, this is a central limit theorem. And here's what the basis of all normal distributions, bell curves are. Random samples greater than 30, then we assume the population, and with the population mean mu and deviation of sigma. Then the sampling distribution, we're going to assume of the sample mean approximates the normal distribution. In other words, we're going to assume the sample mean is the same as the population mean. If I'm given a population mean of 400, I'm going to assume my sample mean is also 400. But if the random sample size n is drawn from a population that is normally distributed, then we got to divide that number by the square root of that sample. So let's go through this. U sample mean equals population mean. U sub x, that's sample mean, equals mu. X squared sub x, that's sample variance, equals the population variance divided by number of samples. And ultimately what we're really looking for is a sample deviation. So sample deviation equals the population deviation divided by the square root of the number of samples. Here's an example right here. Study analyzed the sleep patterns of college students. It is found that the mean amount of sleep is 6.8 hours. That's my mean, that's my average. And the standard deviation is 1.4 hours. Random samples of 100 sleep times are drawn from the population, and the mean of each sample is determined. Find the mean standard deviation of the sample distribution of the sample means. In other words, first we're going to assume is 6.8 hours. That's the mean hour number of sleep in terms of hours the student gets. That's on the population mean, that's the sample mean. We're going to assume the population is the sample mean. The population deviation is 1.4 hours. But we got to find the sample deviation. That is going to be 1.4 hours divided by the square root of 100, which is 10. So my sample deviation is 1.4 divided by 10, which is 0.14. Here's another example. We assume the training heart rate of all 20-year-old athletes are normally distributed with a mean 135 beats per minute and standard deviation of 18 beats per minute. We're going to draw four individuals from all this group of athletes from the population, and the mean of each sample is determined. Find the mean standard deviation of the sample distribution of the means. They've already given us the population mean, 135 beats per minute. So we assume the sample mean is the same. Now, the population deviation is 4. I'm sorry, population deviation is 18 beats per minute. So my population deviation is 18, but I got to divide that by the square root of the sample size, which is 4. And that's 18 over the square root of 4, which is 18. Square root of 4 is 2. 18 over 2 is 9. So my population deviation may be 18. My sample deviation is 9. From what we learned on the previous page, as well as this right here, if we know our individual sample minus our sample mean, that is the same, that we can determine the sample mean and sample deviation, find the z-score for that. It'd be x bar, which is x with a line over it, minus my mu, sample, that's my sample individual minus my mu, over, instead of deviation, the deviation divided by square root of the number of samples, square root of n. Let's look at this one here. A group of drivers between the age of 16 and 19 where the average driver puts 20.7 miles per day on their car. So this could be 1,000 drivers, but we're going to select 50 from that group. What is the probability that those travel each day between 19.4 and 22.5 miles? Assume a deviation of 6.5 miles. Well, if the mean for the population is 20.7, we're going to assume the sample mean is 20.7. Now, the population deviation is 6.5 miles per hour, but we got a sample of 50 individuals. So we take 6.5 divided by the square root of 50, which is 0.919. Square root of 50 is, square root of 49 would be 7. So it's like 6.5 over a little bit over 7, which is 0.919. Now we can find our z-scores for this sample. My lower z-score is going to come from 19.4 miles, that's the lower end, 19.4 minus 20.7 divided by my sample deviation. This is no different from what we did in Wednesday's class. We're just finding out what the sample deviation is, how it affects it. 19.4 minus 20.7 divided by 0.9 is negative 1.41. So I got a z of 1, negative 1.41. Z of 2, which is x bar minus u over the entire population deviation over the square root of the number of samples. That's going to be 22.5 minus 20.7 divided by 0.9. That's 1.96. So when I look it up on the z-score table, my z at negative 1.41 equals 0.0793, and that's going to be on the negative side. And we did 1.96 already. Z at 1.96 is 0.9750. And as we found before, we just take the difference between those two. That's the space in the middle. So 0.9750 minus 0.0793 equals 0.8957, or 89.57% of all the students in this sample go between 19.4 and 22.5 miles per day. Here's another one. Assume the mean room and board expense at a four-year college is $10,453 with a standard deviation of $1,650. We're going to select 9 four-year colleges to determine the probability of the room and board costs less than $10,750. Now that is slightly more than the mean of $10,453. So our mean is 10,053. We're going to assume the population mean, same as standard mean, since this is a normal distribution, as we're told. My deviation is 1,650 for population. I'm going to divide it by 9, square root of 9, which is 3. So 1,650 divided by square root of 9 is the same as 1,650 divided by 3, which is 550. So now my sample mean is $550. And now, since I found that second formula, I can just plug in the z-score, find the z-score of what it is for that $10,750, what percentage that is. 10,750 is the sample I'm looking at, minus my mean, 10,043 divided by my sample deviation, 550. That's 297 for 550, or 0.54. That's going to be in the positive z-score side. And z at 0.54, and I look it up, is 0.7054, or 70.54%. So in other words, 70.54% fall below $10,750 for room and board per year. Now finally, I want to show you this. This is where it gets a little interesting. We look at population probability versus sample probability. It is found that the typical college student pays $1,615 in expenses with a standard deviation of $550. What is the probability that the student will pay less than $1,400? Well, if you go to the bottom here, I'm gonna assume my standard. I mean, my population mean is the same as my sample mean. So 1400, which is less, minus 1650 equals minus $215, divided by my standard deviation. This is for the population, so I'm not changing anything here. 550. 215 over 550, negative 215 over 550 is negative 0.39. And when I look up negative 0.39 on the Z table of negatives, negative 0.39 is 3483 or 34.83%. Now it's asking if 25 college students are randomly sampled. I'm going to use these are all the college students on the left, the population. Now the sample deviation is going to be a little bit different because we're looking at 25 college students. It'd still be 1,400 minus 1,615, which is negative 215. But now my denominator to find the sample deviation is 550 divided by the square number of samples, which is 550 divided by the square root of 25, which is 110. And negative 215 over 110 is negative 1.95 deviations. So what's interesting is with the sample probability, you have a much wider range because smaller groups tend to be more spread out. There's more variation than with larger groups. And that's what this show is here. We'll be going over more of this next week.